All right, now let's classify the equilibrium points of the population model that we've been studying, which was x prime equals 3x minus 2x squared minus xy, and y prime is 2y minus y squared minus xy. And in case you've been following along, this had a very cool application because this models the population of bunnies versus sheep. So population of bunnies versus sheep. And so far, we found the equilibria. So that was done in a previous video. We found, I believe, 0, 0, 0, 2, 3/2, 0, and 1, 1. And now what we need to do is classify them, meaning, first of all, find a gradient. So gradient of f at xy. Again, you differentiate the hell out of everything. So partial 3x minus 2x squared minus xy over partial x. Yes, it's a partial sleigh here. So partial 3x minus 2x squared minus xy with respect to y. Partial 2y minus y squared minus xy with respect to x, and partial 2y minus y squared minus xy with respect to y. Which in this case, as always, it simplifies. So partial f of xy, I believe we get 3 minus 4x minus y. The second one, they're all x terms except the last one. So we get minus x. Similarly with the third term, minus y, and then 2 minus 2y minus x. All right, and now all we need to do is plug in all the points. So let's do 0, 0. So partial f at 0, 0. That is 3 minus 0 minus 0. And then minus 0 minus 0, 2 minus 0 minus 0, which ends up becoming 3, 0, 0, 2. Which, if you want, you can use the determinant trick, but notice this is actually diagonal. Diagonal. So actually you can read off the eigenvalues. So here the eigenvalues are lambda equals 3, which is positive, and lambda equals 2, which is positive. So solutions move away from the origin. So in this case, 0, 0 is unstable. Now let's continue. Let's do, I think, 0, 2. So 0, 2. So let's do the gradient of f at 0, 2. In this case, I think 3 minus 0 minus 2. And then I think 0 minus 2. And then 2 minus 2 times 2 minus 0. Which becomes 1, 0, minus 2, minus 2. You can do the determinant trick, and if you don't know any linear algebra, I recommend it. But it turns out this matrix here is what's called lower triangular. Lower triangular. Which means it has this staircase pattern where in star we have zero or non-zero terms, but everywhere else we have zero. And it turns out for lower triangular matrices, you can also read off the eigenvalues. So here, the eigenvalues are lambda equals 1, which is positive, and lambda equals -2, which is negative. And because we have mixed signs, this is called a saddle. Saddle. And once again, if you're not comfortable with this, just do the determinant trick. If not, it's lower triangular, meaning it has this staircase pattern where this upper right term is 0, and here you can also read off the eigenvalues. All right, now let's continue. So let's do 3/2 0. So let's do the gradient of f at 3/2, 0. So that will be 3 minus 4 times 3/2 minus 0, and then minus 3/2 minus 0, and then 2 minus 2 times 0 minus 3/2. And that simplifies to minus 3 minus 3/2, 0, and 1/2. And once again, you could do the determinant trick, and I would recommend that if you're not comfortable with linear algebra. If not, notice we have this staircase pattern again, but on the other side, and this is what's called upper triangular. Meaning the lower side, the lower left side is 0. So 0 and then star, star, star. And sort of like everything above the diagonal. I mean, in this case, everything below the diagonal is 0. And in that case, we can once again read off the eigenvalues. So the eigenvalues are lambda is -3, which is negative, and lambda is 1/2, which is positive. So 3/2 0 is a saddle. And again, notice I taught you actually 3 things. If the matrix is diagonal, lower triangular, or upper triangular, you can read off the eigenvalues. Everything else is not allowed. In fact, in the next example, we have to do it directly. So case 4, let's do 1, 1. So gradient of f at 1, 1. So that's 3 minus 4 times 1, then minus 1, minus 1, 2 minus 2 times 1, minus 1, and that gives you -2 minus 1, minus 1, minus 1. Call this A. And here, unfortunately, we have to find this directly. So determinant of A minus lambda I, it's -2 minus lambda, -1 minus 1, -1 minus lambda. So -2 minus lambda times -1 minus lambda. minus 1 squared. And so this is, I believe, 2 plus lambda. Sorry, 2 plus 2 lambda plus lambda squared plus 1. And this is lambda squared plus 3 lambda. Sorry. So this becomes 2 plus 2 lambda plus lambda squared plus 1. Yeah. So this becomes 2 plus 2 lambda plus lambda squared minus 1. Took me 3 tries to do that correctly. And that's lambda squared plus 3 lambda plus 1. And here I would say it's easiest to use a quadratic formula. So lambda is minus 3 plus minus 3 squared minus 4 times 1 times 1 over 2. And that becomes minus 3 plus minus square root of 5 over 2. And that gives you lambda is minus 3 minus square root of 5 over 2, which is negative. And lambda is minus 3 plus square root of 5 over 2, which is, turns out, is also negative because 3 is square root of 9, which is bigger than square root of 5. So you're subtracting something from square root of 5 that's bigger, and so you get negative, and therefore 1, 1 is stable. And so our conclusion is that 0, 0 is unstable, 0, 2 is a saddle, 3/2 2 is a saddle, and then 1, 1 is stable. In other words, we have the following picture, which we will complete in the next video. We have 0, 0, which is unstable. So arrows go out of 0, 0. We have 1, 1, which is stable. So things go in. And we have 3/2 0, so 1.50 and 0, 2, where one direction is going in, the other one is going out. And we will see in the next video that the orientations have to be like that. So this is going in on one side, going out of one side, and also going out on one side, going in on one side. And as I said, in the next video, we will complete this picture a little bit more to figure out what happens to our population model.